Well, hello. I'm going over rational functions. Currently, nobody's here. Maybe they're out celebrating St. Patrick's Day. I don't know. Or maybe they're like me and staying inside because we're supposed to get snow. Anyway, rational functions. So, what is a rational function? So, we've already talked about rational expressions, where you have variables in the denominator, and we've talked about the set of rational numbers where it's a number that's a fraction. So a rational function is specifically a function that has a rational expression. So remember that a function means for every input there's one output. So it's a special type of equation or rational equation, specifically where one input gives you one output. So we usually write this with P of Q over Q of Q, P of Q, P of X over Q of X, and then that should be Q in the denominator. Those letters aren't even next to each other on the keyboard, so I'm not sure why I write D. Maybe I was thinking denominator. But usually P stands for polynomial, Q stands for quotient, so they just write it as P over Q because that's also the type of language that's used for writing rational numbers. They describe it as P over Q, and then we also used P over Q when we were talking about the rational zero theorem. So just consistency, when you have a fraction, we're using P over Q, but we're using P of X and Q of X to indicate that these are polynomials. They are functions, so the top and the bottom are both functions of their own, basically. So we talked about how we had function division. A rational function is function division. It's a new function created by dividing two other functions, specifically polynomials. So a lot of times you're asked to analyze a rational function. Analyzing something is really figuring out what do all the pieces mean. And so when we're doing this with rational functions, we're often looking at, well, what does it look like when we graph it? What's the general shape? Where are the asymptotes and what are the asymptotes? So you'll learn what those are. Where are the intercepts, the x and y intercepts? What is the domain and what is the range? Those are the typical things when you're asked to analyze rational functions. When you're analyzing any kind of function, you're always looking at the shape. With polynomials, we also looked at end behavior, intercepts, zeros was something specific to polynomials, but each type of function. And the key to understanding functions is that these are things that we like to look at in graphs. So when we talk about functions, we usually like to graph them. And so you're looking at various aspects of the graph and understanding what the graph means. And these are helpful pieces of information when you go into linear programming or any kind of modeling. You're using these aspects. And calculus, if you have to go on to calculus, you're looking for maximums and minimums. You're doing a lot of analysis of graphs. So that's what we're doing here. So there are two basic shapes of rational functions. We've got the left and we've got the right. So the left is what happens when you have 1 over x, or basically your denominator has an odd exponent. So if it's an odd, you can see we got two different sections of the graph, and they're almost reflected across y equals negative x. So y equals negative x would be this line right here, and they form a mirror image. If you were to put a mirror right there, it reflects across that line. And it gets really close to both the x and the y axis, but it doesn't actually hit those. If you zoom in, if you graph this in decimals and you zoom, you'll never actually touch any of the axes. You get really close to it, but you won't touch it. On the right is what happens when you have an even exponent in your denominator. Basically, instead of being a reflection on the diagonal, it's now a reflection across the y-axis. And so it looks symmetric, but again, it gets really close to the axes, but never actually touches the axes. So these are the two basic shapes. You can see some variation. Sometimes there's a third piece and you've got some stuff going on in the middle of the third piece. Sometimes you have these kind of rotated, but these are the two basic shapes of rational functions. So one of the other things that we talk about when we analyze rational functions are asymptotes. So what are asymptotes? So it's essentially the word has a silent P. Oh, I slightly say asymptotes, but it's basically like a silent P, asymptote. And the dictionary or spell check always tells me this word doesn't exist. It exists, it's just for whatever reason not in spell check. But what these are lines that your graph goes near but never actually touches. So if I go back to my graphs here, and let's choose, like if I, you can't really see that. Let me choose a different color. I'll just use blue. So basically the x-axis, we talked about how you get close to that, but we never touch it. That is an asymptote, and that is called the horizontal asymptote because it's a horizontal line. And then the y-axis, we get close to it, but we never actually touch it with our graph. That is called the vertical asymptote because it's a vertical line. And so we generally have two different types of asymptotes, horizontal and vertical, and it's like what happens, it's a line that your graph gets really close to but doesn't touch. So these are basically sometimes called limits. So when you go into calculus, you learn a concept called limits, and a limit is basically you're asking yourself what happens to my graph, or what happens to the y value as I head near this x value. And so that's what's called a limit. Where is my graph heading, essentially? And so asymptotes are a type of limit because it's like, okay, as my x values go towards like negative or positive infinity on the way outskirts of the horizontal axis, what is happening to y on my graph is getting towards 0. So that would be your asymptote at y equals 0. And you can also, well, as y gets really, really big or small, what happens to x? Or as x goes to 0, what happens to my y values? So that's what the limit is. It's basically, you're looking at, as I head towards somewhere on my graph, what is the other variable doing? So I already talked about vertical and horizontal asymptotes. There's also slant asymptotes, and those are asymptotes that are actually, instead of horizontal and vertical, they're slanted lines. So those exist. Sometimes you get fancy asymptotes that are parabolas, but that's, those are not very common. And asymptotes are also called the behavior of the function. Basically, what happens to the function as different things occur. It's very similar to end behavior, where, okay, as we get towards infinity, what is happening to my graph? So asymptotes are related to end behavior in a way, and end behavior and asymptotes are all related to this concept of a limit that you talk about in calculus. And actually, you talk about another version of the limit in pre-calc, but you don't call it as much. So to find the asymptotes, it's actually pretty simple. So the vertical asymptote is anywhere your denominator is equal to 0. And so whatever value is excluded from your domain, that's where the vertical asymptote occurs. Horizontal asymptotes and slant asymptotes are basically what happens as x goes to infinity or negative infinity. Those are found a little differently. So those are going to be total different slide because there's actually a procedure. There's like, if you're into programming, you understand if statements. There's basically like an if statement thing you have to go through to determine how to figure out your asymptotes there. But the vertical asymptote is really easy because it's wherever your denominator is 0. So limit notation. This is something that is introduced in our textbook here as a way to indicate what happens. It's a shortcut to try to explain what we're talking about. So these are the 4 different types of notation you commonly see. And so you've got x, you've got this little arrow, a right arrow, and then it says C+. This is telling us, okay, as your x heads towards this number C, and the plus means it's from the right side, because that's the positive side of the graph. So if you're heading towards it from the right, you're starting at infinity and then you're getting closer this way. That's what it means to come from the right side. You're coming from the outside of the right and you're heading towards the middle. So that's what that notation means, is x is heading from outside to the middle of the graph. What happens to y, basically? When you have that same thing but with a negative, that just means you're coming from the left side. So you start at the left side of your graph and then you head towards the middle. And that's the negative side of the graph, so that's why they use the negative sign there. And these are actually exponents. They're written as superscripts or exponents here in the notation. Then we've got x to infinity and x to negative infinity, and these are actually where you're starting in the middle of the graph. You're starting at the center, like at 0, and then as you head to one side or the other side. So as x starts at 0 and then heads towards positive infinity, you're looking at what happens to y, and then as x starts at 0 and it goes to negative infinity, what happens to y. So you're basically going towards a number, you're starting at the infinities and you're going in the middle, and then when you're heading towards infinity, you're starting in the middle, you're going the other way. But these are just different shortcuts to explain this, because otherwise you'd be writing in words. What happens to y as x goes to 5 from the right side of the graph? It's a lot of words to write down. That's why we come up with notation. So that's what that notation means. You'll see this again in pre-calc. You'll see it again in calculus. So if you're heading that way, definitely take note. It's just really nice shorthand too, just even if you're not going that way. So I wanted to do an example here where we practice some of this notation. And as we practice this notation, we're actually finding the asymptotes. So you're kind of doing two things at once here. So we've got a graph. A lot of this stuff is all done graphically, so make Desmos your best friend. Graph the equation and then we'll look at the graph. So find the limits or behavior, and that's another term, so the questions might say find the behavior for f of x equals 1 over x based on that graph. So we have the graph. And then I've got as x heads to 0 from the right side. So that means I'm starting at positive infinity and going towards 0. F of x, and then we have this arrow. So that's saying, okay, where is our y value going? Because remember, f of x is equal to y. Those are the same thing. So think of it, where is y going? So as I head towards 0 here from the right, the y value, you can see on my graph, is going really high up. And it's going to continue and go up to positive infinity. And so we stop at 0. We don't go past 0. But as I'm heading from the right side because of the plus, my y value is going all the way up. So that is heading towards positive infinity. The next one says as x approaches 0 from the negative side. So now we're going from the left side of the graph heading towards 0. So as I head towards 0, what happens to my y value? Well, my y value, my graph is actually going really down, going down to negative infinity. It's going as down as it can go. So we say that f of x approaches negative infinity. Now as x goes to infinity, so that's basically you're starting at 0 now, and you're saying, well, what happens as I now go in the opposite direction as I go to the right towards infinity? My y value is getting really close to 0. So you can see it's getting closer and closer and closer to the middle of the graph. So we say that f of x approaches 0. And then we have as x goes to negative infinity. So you start at 0, and then as your x goes towards the left side of the graph, the negative portions of the graph, what happens to y? And our y value is getting really close to y equals 0. So f of x approaches 0. So approaches is another term for reading that arrow. So you can read that as approaches. But that's what this is doing here, is it's saying, okay, what happens to these various things? And 0 here, I'm going to just make a side note. Now y equals 0 is the horizontal asymptote. And so that's specifically, as we're going towards infinity, negative infinity, what has happened to y? It's getting to 0. That is considered our horizontal asymptote. And so it approaches 0 from both sides. No matter if you're going to the right or the left, you're still getting towards 0. You have that line, y equals 0. Now, the x equals 0. So notice that as x approaches 0 from either side, we want to positive infinity and negative infinity. So think of that as sort of the inverse, or the opposite of the horizontal asymptote. So x equals 0, which is as we're approaching 0 from either side, we went to crazy infinity and negative infinity. So the x equals 0 is called the vertical asymptote. So if you think about it in terms of inverses, we talked about inverse functions where you flip-flop your x and y. So if you flip-flop your x and y, and in this case also flip-flop the order of what you're asking here. I don't know if you can kind of visualize in your head what I mean by flip-flop, but where, you know, I have the setup here, our infinities and negative infinities are now, they were with the f and now they're on the x, and then the zeros were with the x, now they're with the f of x stuff. You can see how they kind of flip-flopped. Like in inverse, it kind of, the x and y sort of switched in that case. But you can think of that sort of our horizontal and our vertical asymptotes are sort of flip-flopped in this way. Hopefully that didn't confuse you further, but I'm just trying to make a connection here between the vertical asymptote is what happens when y goes to infinity, while the horizontal asymptote is basically what happens when x goes to infinity. If that I should write that down. That just came to me, and that is exactly what we're looking at here. So vertical asymptote as y goes to plus or minus infinity, basically that's what's called the vertical asymptote, while the horizontal asymptote is where x goes to plus or minus infinity, and that's what makes it a horizontal asymptote. So let's take a look at this graph. So this is a completely different graph, and so our function is f of x equals 2x over x minus 4. So we're just going to use the graph to figure out these values that I'm asking about. So we've got as x goes to 4 from the positive direction. So first we need to figure out where 4 is on the graph. So I wish I had it a little bigger. But 4 is right there where I drew my vertical line. And I'm actually going to make a vertical line as best I can, just so you can visualize that x equals 4 line here. Okay, that was really terrible. I started touching 5. Really hard on a very small graph, very small grids. Okay, as best as I can. So we're now approaching 4. That is the line that we're looking at here, x equals 4. So as we're heading towards this from the positive side, 4 plus means 4 from the positive side. So I'm going from the outside of the graph towards 4. What happens to y? Well, our graph is going up again towards positive infinity. Now, the next one says x goes to 4 from the negative side. So that means we're coming from the left side going towards this line that I drew at x equals 4. And when you do that, our graph on that particular side of the line is going down, so that's negative infinity. And again, because the y values are going to infinity, this is what's called the vertical asymptote. And this asymptote is at this point x equals 4, at that line where it appears to go to infinity and negative infinity. So that's what makes it a vertical asymptote. So now I'm going to erase so I can draw for the next part. So the next part is what happens as x goes to infinity. So that means you're starting at the center and then we're going out to the right. So you can see that our graph is approaching something. It's not 0 because it's above the horizontal axis. What x value does it look like it's going towards? So it's kind of hard to read on my graph here, but this is 1, 2, 1, 2. So 2 is right here, and so it looks like it's basically almost hitting 2 right there. And so we'll say as x goes to infinity, our f of x is approaching 2. So that looks like where it's basically, we try to make these whole numbers. So you want to get the closest whole number. The closest whole number there based on that graph is x equals, or y equals 2. Now the next one is x goes to negative infinity. So now we're going the other direction. We're starting at 0 and we're going to the left, to the negative side. And our graph, if I stretch out that y equals 2 line, it actually almost looks like we're on top of the picture that I have. So it's approaching 2, again, the y value of 2. And this is what is the horizontal asymptote, which is what happens when x goes to infinity. So the horizontal asymptote is y equals 2, because that is the y value that the numbers seem to be approaching from either end as you stretch out. So when you're looking at the graph, you're kind of looking for these horizontal and vertical lines that seem to line up with where it goes to infinity. And those are basically the asymptotes. So vertical asymptotes, here's the official definition. So the line x equals c, where c is just a constant, is a vertical asymptote of the graph of f of x if f of x approaches infinity or negative infinity as x approaches c from either side. So this matches what I wrote here as y goes to infinity or negative infinity. It's a vertical asymptote, whatever that number is. So we've got some examples here of what it can look like, just so you have visually what that vertical asymptote means from various sides. So to find the vertical asymptote, you first factor the numerator and the denominator and simplify. Because, well, as I say every week, we factor all the time. But if things cancel out on the top and the bottom, those are no longer asymptotes. They're now considered holes in the graph, but they're not actually an asymptote. So we have to factor in order to cancel things out, to put it in simplest form in order to find the vertical asymptotes. So that's why we had to learn how to simplify fractions, simplify rational expressions. So after you've done that, you've reduced, you cancel things out, you set the denominator equal to 0, and then we solve that, and that will give us our vertical asymptote. And usually your denominator is a linear or it might be quadratic, and so you could get 1 or 2 vertical asymptotes. It's possible to have, you can have as many vertical asymptotes honestly as you want, but most of the time there's only 1 or 2. Those are the most common types that we see. We don't normally, I don't think I've ever actually solved a problem where there's been 3, but it's possible. So that's why we had to learn how to solve for x, and we had to learn how to solve quadratics, because those are the 2 things that you end up with in the denominator. So that's how you find the vertical asymptotes. And the vertical asymptotes are actually used to also tell you the domain, essentially. The domain is slightly different because we have those holes to worry about. So the difference between the two, because they're very similar when you're looking at rational expressions and rational functions, is that the domain is all values for x except those that make the denominator 0 before you factor and solve, or factor and simplify. You can find it after you factor, but before simplifying. The key is it's before simplifying. So I should actually just before simplifying, because you do want to factor to find the domain. So it's before you start canceling things out. And then you write your domain in interval notation. Vertical asymptotes, on the other hand, are found after the simplifying, but you're still factoring. So that's the difference. One's found before, one's found after. And then those are written as equations. So one is written in interval notation, one is written as equations. The numbers are almost exactly the same every time. So that's why people get confused, because your domain might be all values except x equals 2, and then your vertical asymptote is x equals 2. So they're very similar, but it's how you write them that's different. And there's slightly different ways of finding them, and that before and after simplifying does matter, because there are things that show up in the domain that may not be asymptotes. So let's just find the vertical asymptotes here. and the domain so you can see these different examples. So first example here on the left is already factored. There's not really anything to do. It's simplified. We have 2 over x plus 7. So it's simplified. There's nothing we can do, so we can find the domain and the vertical asymptotes at the same time. So here's how I basically do it. So domain is where the denominator is not equal to 0. So I should actually write the denominator. So the denominator cannot be 0 to find domain. So x plus 7 cannot equal 0. And so then I solve for x. And so this says that, oops, I want blue, not green. X cannot equal -7. So that means -7 is not in our domain. So the way that we put this in interval notation is we use the union. So you have -infinity to -7, parenthesis, union -7 to infinity. Because we can't include -7, so we have to have parentheses. And then we have 2 pieces because we have that gap. Remember, the graph is 2 separate pieces. So when you have 2 separate pieces of the graph, you have to use a U to combine them for your domain. And then the range is that same denominator, but now you want to know where is it equal to 0. So notice that it's basically the same exact process. Now you want to know where is it equal to 0. So again, we do the same thing. We're subtracting 7 from both sides. Almost exact same. And wait, why did I say range? Vertical asymptote is what I'm trying to say. That's what we're doing here. Sorry. Vertical asymptote. I'm so used to doing domain and range together. So vertical asymptote is basically you take the same thing you did for domain, but now it's equal to 0. And now we get x is equal to -7. So our vertical asymptote is an equation. So our equation is x equals -7. So that's what you do. So on the right here, now we have something that we need to factor before we can find the domain and the range. So we just use g instead of f because it's a new equation, new function. So I'm going to factor this, and +3, I minus 1, there we go. Okay, so I just factored it, factors to x plus 2 over 3x minus 1 and x plus 3. So we factor, domain is found before you simplify. And so that's, you have 3x minus 1 times x plus 3 is not equal to 0. So we have a quadratic equation here. We're solving by factoring. Even though it's a not equal sign, it doesn't matter. You do the same thing. So you set each part, in this case, not equal to 0. And then you solve. Now I'm kind of running out of room here, so I'm going to just leave the solving for you and give you the right answers, because I don't have a lot of space here. We got x equals 1/3, and then x equals -3. So here we've got 2 numbers, or x not equal 1/3, x is not equal to -3. 2 numbers that we're not allowed to have in the domain. So this means now we've split it up into 3 separate pieces. So I talked about how sometimes there's a third piece. So if you have 3 separate pieces, you need them all separated out by union things. And you always have the smaller number first. We go from -infinity to -3, because that's the smaller of these 2 numbers. Union, then we have -3 to 1/3, and then we need to go 1/3 to infinity. So we've got 3 separate pieces here. Now the vertical asymptote is found after you simplify. So after you try to cancel things out. We don't have anything we can cancel out on the top or the bottom because x plus 2 doesn't have anything in common with the denominator. So there's nothing here that we can cancel out. So your vertical asymptote, which I always abbreviate VA, that is where your denominator is equal to 0. And basically, you solve it the same way. You're going to get two vertical asymptotes, one at 1/3 and one at -3. So you can see the relationship between domain and vertical asymptotes here is the numbers. The numbers are exactly the same. One is a not equals, one is an equals, and how you write your answers are slightly different. Okay, so here we've got, again, we're going to find vertical asymptotes and the domain. So on the left, we need to factor first. We have f of x equals x minus 5. You're probably hearing that tapping. Sometimes that comes up on I have a very good microphone. It takes every noise. X over 5, and then the denominator factors to x plus 5, x minus 5. So I'm not going over the factoring because that's something that you can do on your own. The goal here is to focus on the asymptotes in the domain. So if you need to fill in the factoring points for your own notes, go ahead, fill that in, do the factoring yourself, and then you can have those steps. So the domain is found before we simplify. So my domain is where x plus 5 and x minus 5 do not equal 0. So that means x plus 5 cannot equal to 0 and x minus 5 cannot equal 0. Let's make sure I'm on the camera. So when you solve these, you get x cannot be -5, x cannot be 5. And so this is going to be another three-piecer when we write our domain. -infinity to -5, union -5 to 5, union 5 to infinity. You're going to see a pattern when you do enough of these on how to write the domain, how to write the vertical asymptotes. Now the vertical asymptote you do after you cancel things out. So notice that we have an x minus 5 on the top and the bottom that we can cancel. So the only thing left in the denominator is x plus 5. So that's the only thing we look at for the vertical asymptote because we've canceled out x minus 5. So you get x plus 5 equal to 0 because you set your denominator equal to 0. And this will solve and get you x equals -5. So we have one vertical asymptote, but two things that are excluded from the domain. So the one that we canceled out is called a hole in our graph, where if you graph it in Desmos, it will look like it's actually connected, but it's not. There's actually a little tiny hole at x equals 5 that you won't be able to see. And actually, I'm going to pull up Desmos and graph that for you guys. So make sure that way you can see what I'm talking about. Let me pull this over. Okay, so we do f of x equals, and then I hit the slash first so I can get my fraction set up. X minus 5, x squared, whoops, x squared minus 25. Okay, so this is what the graph looks like in Desmos. And so we have our vertical asymptote at -5, which is actually right here. I can actually put in x equals -5, and I like to do my vertical asymptotes as dashed lines. So you can see that the graph is approaching it as it heads towards this vertical asymptote. The y values are basically going to positive and negative infinity. Now, x equals 5 is a hole in the graph. So it doesn't look like there's a hole in Desmos. It graphs it continuously. But if I actually go to 5, So notice it's a solid dot. I don't know if you can see that really well, but there's a solid dot until I get to 5. And then it turns to an open circle and it's undefined. So it's a hole in the graph. Desmos just doesn't really show that well. So it's not a vertical asymptote because it canceled out. It's just a hole. And I don't think, even if you zoom in, Desmos still will connect it, even though it's not connected. So just be careful that you can't always trust a graph for domain or technology for a domain, because it may, the way that the system shows it is that it graphs it as if it's continuous, even though it's not. There's actually a gap there. So that's the example on the left. Now, the one on the right, I need a factor, so g of x equals 18x. And the denominator, actually, x squared plus 100 does not factor. If it was x squared minus 100, it would factor. But that is actually a sum of squares, and those don't factor. So if you can't factor, then you go straight to finding your domain. So your domain, you set the denominator, so x squared plus 100 not equal to 0. And now we're solving this equation. So I'd be subtracting 100 from both sides. So that gives me x squared equals negative 100. And we're solving a quadratic. We'll solve this by taking square roots. So I'd be taking the square root of both sides. And notice I'm taking a square root of a negative. So we're going to get a complex number. So we get plus or minus, and this will give us 10i. Now, everything when we think of domain, we're thinking in terms of things we can graph. So, oops, and these are all not equal. So if you get imaginary numbers, you can't graph those. So if you solve something like this and you get imaginary numbers, that tells you your domain is all real numbers. There's not really anything excluded because the excluded stuff can't be graphed anyway. They're imaginary. So our domain is all real numbers, negative infinity to positive infinity. And then for your vertical asymptotes, you take that same denominator, because there's nothing to cancel out. You set it equal to 0, and so when we solve, we will get x equal to plus or minus 10i. Now again, we can't graph complex numbers. We can't graph imaginary numbers, and a vertical asymptote here is telling us that it's at an imaginary number. So this would say there's no vertical asymptotes. Because it's imaginary, we can't graph that. Now, when you get to calculus, and if you're in engineering, these are actually called poles. Poles are a special type of graphing in the complex plane where you can graph things with imaginary numbers, but we're not there. Right now, we're only looking at graphing real numbers. And so here our domain is all real numbers, and there is no vertical asymptote. So I can pull up Desmos again and put in our function here, g of x equals 18x over x squared plus 100. So this is what it looks like. And if I zoom out, there is a horizontal asymptote, though we haven't talked about how to find those yet. There's a horizontal asymptote, but there's no spot where it goes to infinity in the vertical or direction in either way. So there's no vertical asymptote, and it looks, it looks like there's no gaps. You can only know that for sure by the algebra portion, as I talked about. But this is what this one looks like. So this is doesn't even look like our typical rational function, and that's because of the fact that it doesn't have any asymptotes. So let's talk about our asymptotes, the horizontal slant ones, because we haven't been finding those yet. We haven't done anything with those. So that's what happens when you're looking at infinity on the x and the y instead of y here. And so this is where you basically have an if statement that you're looking at. So if the degree of the numerator, so that's the highest exponent on the top, is larger than the degree of the denominator, which is the highest exponent of the denominator, that's when you get a slant asymptote. So when the degree of the top is larger than the degree in the bottom, then it's slanted, so it's going to be angled. This is also called an oblique asymptote. So that is another terminology sometimes you'll see. Depends on the textbook on how they describe that. Otherwise, it's going to be horizontal. So there's only one particular case where it's going to be slanted. And so these are just visually examples of what the horizontal looks like, the horizontal asymptote looks like when you graph it. So I kind of did my best to come up with this if statement kind of thing to find these horizontal and slant asymptotes. So the first step is you need to figure out the degree of the top and the bottom, but you need to simplify first. Just like we had to simplify it to find the vertical asymptote, you have to simplify to find the horizontal asymptote. So once you've canceled things out, if things cancel out, then you find the degree of the top and the degree of the bottom, and then your choices are either the top smaller than the bottom, it's equal to the bottom, or it's greater than the bottom. If the highest exponent on the top is smaller than the highest exponent on the bottom, that's the degree, your horizontal asymptote is y equals 0 every time. So you don't even need to do any thinking, you don't have to do any solving, you recognize that and you say, oh, it's 0 every time. If the degree of the top is equal to the degree of the bottom, it's actually taken from the leading coefficient. So you just take the numbers in front of those highest terms. That is your horizontal asymptote. So again, you don't even really have to do any work other than simplifying in case it's a fraction. It's just literally the numbers in front of them. When it's a slant asymptote where the degree of the top is larger than the bottom, we need to do long division, and your asymptote is the non-remainder part. So that's what's called the quotient. It's the part before you have the remainder. So that does take some work because you do have to do long division to find that particular asymptote. But that is not as common. Most of the time it's one of the first two, and those are actually really, really easy. Like, rational functions are way easier than polynomials. It really is. So let's look at some examples. We're just going to find the horizontal and slant asymptotes. So we're looking at the degree of the top and the degree of the bottom. And then you do want to simplify first. So first we need to factor, if we can, cancel things out. So actually, because I just have a number 8 on the top, if I factor this, nothing's going to cancel out. So we can go straight to the horizontal and slant asymptotes. And so we want to the degree of the top. So what is your highest exponent on the top? Well, we don't have an exponent on the top, so that's assumed to be degree 0 because there isn't even an x on the top. If there was an x, we'd call it degree 1, but we just have a number, so that's 0. And then our degree on the bottom is the highest exponent, that is 2. So the degree of the top is less than the degree of the bottom because 0 is less than 2. So we just go to our chart here, horizontal asymptote is y equals 0. Bam, done. So horizontal asymptote, y equals 0. Didn't even, I mean, there's like no math involved. You're just looking at the numbers. Super easy. Now let's look at what we have on the right. So let's see, the denominator is not going to cancel because it's got x squared plus 2. And I know that if I attempt to factor the top, nothing's going to cancel out. So we're just going to look at the degree of the top. So the highest exponent on the top is an x squared, so that's 2. And then our degree on the bottom, highest exponent is 2. So our top is equal to the degree of the bottom. So I go to my chart here, my little table at top equals bottom. The horizontal asymptote is formed from the leading coefficients, A over B. So I'm going to highlight those, the leading coefficients in front of those x squared terms. So that's -4, and then we don't have a coefficient here, so that would be a 1. So I abbreviate horizontal asymptote as HA, just like vertical for VA. So it's y equals -4 over 1, which you simplify and you get -4. So a little more work because you have to get the numbers in front of the x squared terms, but then you just simplify, and that's your asymptote. So I'm going to graph these so you can verify, and you'll see, let's look at the graph so you can believe that these are true. So let's graph the first one. Q of x equals 8 divided by x squared plus 4x plus 4. Okay, so horizontal asymptote was y equals 0. So we're looking at just the horizontal. We didn't even talk about the vertical asymptotes. You can see that there is one, but we weren't finding those. Horizontal asymptote, y equals 0. You can see that at y equals 0, which I could graph here, the black line. Let's make that orange and dash. You can see that our graph is approaching that line, and they're basically almost on top of each other here. So that matches with what the vertical or the horizontal asymptote is. Now our other one, r of x equals, this is going to be a complicated one, -4x squared plus 5x minus 1 over x squared plus 2. Okay. And we found our horizontal asymptote at -4. So I'm going to change this y to -4. And so now you can see where there's no vertical asymptote here, but we do have a horizontal asymptote. And you can see that as we go towards the outside parts of our graph, it's approaching that y equals -4 that we solved for. It's getting close to that line. And as I zoom out, you can see that it actually looks like it's right on top of it. So what we did with our algebra matches with what the graph is telling us. The graphing takes more time to graph it because you got to type all that in. With the algebra, you're just counting and then you're just writing the numbers in front, like super, super easy. Okay, now these two are going to be slant asymptotes because the degree here is greater on the top than it is on the bottom. And these are not designed to, I don't believe these factor. So let's look at q of x here. Actually, I don't need to write it down. So q of x, I know that one's not going to factor. So we can go straight to the degree of the top, which is the highest exponent's 3. And then the degree of the bottom is 1 because it's linear. So but it does have an x, so that's going to be 1. So our top is greater than the bottom. So if I go back to that decision tree thing that I have, when the top is greater than the bottom, a slant asymptote is found by doing a long division. And then your answer is y equals the part that's not the remainder. So we have to do long division on this problem. So that's why we had to learn how to do that. And this is the part that takes a while. So I have to take the top, which I don't have an x term, so I have to add in a 0 there. And then I'm dividing it by 2x minus 3. So in the interest of time, because it's already been 50 minutes of this video, I'm not going to explain the division part here in the long division. You can go to the videos on long division to fill this in. So if you are struggling when you're taking notes on this video and you're like, I'm not following this, you can pause this, go to the long division stuff, fill that in, fill in extra steps as needed, and then you can come back to this video after I've done this. So that's what I would do to kind of fill in, because I do have to skip some steps here in the interest of time. I can't explain everything. So let's see. So this is going to be 2x squared. Whoops, not 2. That's going to be 1/2. This is actually going to be a tricky one. That gives us x cubed minus 3/2 x squared. Subtract, change the signs. 1 plus 3/2, so that's 2 plus 3, it's 5/2. Nope, that's a -1. -3 minus 1, so that is 1/2 x squared. Drop down. Now to get to, I need to multiply that by 1/4 x. This is actually a tricky long division one. I should have picked a different one. 2/4, so that's 1/2 x squared minus 3/4 x. Change my signs, running out of room. So we got 3/4 x plus 1. Now that's going to be 3/8. And then, okay, so I'm kind of running out of room here, but the next part is going to give me the remainder. So what I have on top here, I've kind of squeezed in, that is our slant asymptote. So the slant asymptote here is y equals 1/2 x squared plus 1/4 x plus 3/8. So again, I went through this long division very quickly. You're going to want to fill that in on your own. So let's bring this up on the graph so you can see what this looks like. It doesn't really matter what my function stuff is, just that I have x cubed minus x squared plus 1, and then this is 2x minus 3. Okay, so I'm going to just turn this off. So this is a really interesting looking graph here. So you can see that we've got what looks like maybe a vertical asymptote here. You see how it kind of, but it does some really interesting things. So our slant asymptote, this is one of those ones where I said it's possible to get a quadratic or a parabola. Most of the time they're lines. This one is a parabola. Whoops, make sure I actually enter it in right. So I'm just putting that in for my y, I turn it on, and you can see that how this part kind of follows a parabola here. When we did that line division, that is the parabola that it's following. And that is, it's called a slant asymptote because usually it's a line. In this case, it's a parabola. But that is, we don't have a horizontal because we don't have a straight line we're approaching anything. We do have a vertical asymptote here, but we have this slant or oblique asymptote following the parabola, and we found that from long division. So this is probably should have started with the one that actually comes out with the linear here versus a cubic or a quadratic, because this was, you know, then you'll actually see that it's slanted. But that's, you go through the long division process. So finding intercepts of rational functions. So that's the last thing of the analyzing that we haven't talked about. We've talked about the domain. We didn't really talk about the range, not as important. We talked about asymptotes. When you're analyzing it, we talked about shape, but we haven't talked about intercepts. So when you're finding x and y intercepts, the rules for finding the intercepts are completely unchanged. They're the same as when you're finding them for every other function. So to find the x-intercepts, you just plug in f of x equals 0. You set y equal to 0. So you set your equation equal to 0. And what happens is when you multiply both sides by the denominator, which is what we do when we're solving rational equations, the denominator, you still get 0 equals something. You get 0 equals the top. So to find the x-intercepts, you just take the top of the fraction, set it equal to 0, and solve. So you don't even need the denominator when you're finding the x-intercepts. Now, to find the y-intercepts, that's where you plug in 0, x equals 0. So then you replace x with 0, and then you're just evaluating the right side. So then you're following the order of operations on the right side to find those intercepts. So not same rules that we've been doing, there's just for the x-intercepts, there's a shortcut that can save you some time. You just set the top equal to 0 to find those x-intercepts. So that is everything. This is basically, there's 2 sections on rational functions. The second one has some applications, but this is basically everything that you learn in those two sections. It's really, once you do enough of them, they're not hard at all. The hardest part is just the long division. And if you need help on that, you can go back, and that's only when you have the top greater than the bottom that you need to do the long division. So thank you for sticking through watching this entire hour-long video. Probably going to have to cut it up into multiple videos next time. But hopefully this is helpful, and I will talk to you guys later. Bye.